Hi Level 3s. Today we'll look at torque and rotational inertia, but before we do, let us go back and check what we've done already. We looked at the difference between circular motion and rotational motion. We looked at what is an angular measurement. So remember, displacement is measured in radians rather than degrees, and a radian is about 57 degrees, and there's 2 pi radians in 360 degrees, which is 1 revolution. We also saw that angular velocity, omega, is measured in radians per second, and we also saw that the relationship between any linear relationship, like linear displacement, and its angular component or counterpart, like angular displacement, is simply the value r in all 3 of these equations. You can relate linear to rotational or angular measurements. Also at the top here looked at the formula for angular acceleration. It's measured in radians per second squared. We looked at the graphs that are similar to translational motion graphs, and we also took a look at the equations of rotational motion. So let's use those ideas to continue looking at torque and rotational inertia. So first up, what is torque? Just a gentle reminder, if a force is applied close to the line or the axis of rotation of the force, then the torque will be, or the force needs to be large because the torque will be small. But if you apply the force a distance away from the axis of rotation, then your torque will be large. So it's the turning effect of a force. That's called a torque. Here we have an example of a wheel that's fixed at the center, and there is a piece of string wound around this axis in the middle, and so only the force of the mass, force of gravity on the mass, causes the turning effect of the wheel. So what happens is that this force due to gravity creates a tension in the string, and the unbalanced force then creates the angular acceleration. So we can work this out by F net equals ma, and a is equal to r times alpha, which is the angular acceleration. So we can calculate the angular acceleration. We can also calculate the rotational inertia from this equation down here. So just note that F net equals Fg minus T, so net or unbalanced force equals the weight force minus the tension in the string. And so you end up finding this net force as well to calculate your values. Here is an application of gears and torque. So bicycles use gear ratios to change how the force put into the bike is used to make the bike go faster. So essentially, gear ratios in a bicycle will change how far the rear wheel will turn for every turn of the pedals. So imagine you're going up a hill. No matter which gear you're in, you'll have to travel the same distance and ultimately use the same amount of net force. But if you shift into a lower gear, you can make it up a lot easier, because the wheel only turns a short distance for each rotation of the pedals. So in this way, the force that you need to move a few centimeters forward on the road is spread over the entire turn of the pedals, making it easier to concentrate a lot of force into a short distance. Less force is required to produce the torque. And you would have known that if you try and climb a hill with a higher gear, then each rotation of the pedal turns the wheel 2 or 3 full rotations, and it's much more difficult to pedal the bike up the hill. This is because while the force needed to push the bike up the same stretch of road would remain the same, it would be spread out over fewer turns of the pedals, so you need more torque to move the pedals the same distance around. So right now, it's a good idea to go look at the examples in Bendel, page 137, and then we'll continue on to rotational inertia. Let's just compare linear, or let's start with what we know. So linear inertia, from Newton's second law, we know that a net or unbalanced force acting on an object causes an acceleration, right? So force is inversely proportional to the mass of the object. We also know, down here on the left, that an object's mass is a measure of its inertia, or in other words, its opposition to change its velocity, whether that's because it's already moving and you want to slow it down, or it's at rest and you want to get it going. So rotational inertia is similar. An unbalanced torque causes angular acceleration, so T equals I times alpha, and normally this would be F equals ma. Now it's torque equals I, which is rotational inertia, times alpha. And an object's rotational inertia I determines its opposition to changes in angular velocity, and the unit is kilogram meter squared. So rotational inertia is similar to the mass of an object. The mass of an object, rotational inertia depends on the mass of the object. So the more mass, the more rotational inertia it has. And it depends on the distance of the mass from the center of rotation. So if there's more mass further away from the center, that would increase its rotational inertia. So rotational inertia I is proportional to the distance squared. Looking at the two diagrams on the left, you can see that the masses of the top diagram are further away from the center of rotation, and so this will have a large rotational inertia. So it will turn quite slowly because the masses are further from the center, whereas here the masses are closer to the center, and so it will spin faster with the same mass, causing it to rotate. Similarly, if we have two discs or two objects, both the same diameter, but the one is hollow and the other one is solid, they have the same mass as well. Which one will hit the ground? Which one will hit the bottom of the ramp first? And it will be the solid one because it has the smaller rotational inertia. So there's more mass closer to the center. And then rods of equal mass, m, and length. So here you have two rods. This one spins through the middle, and this one spins so that the mass is spinning around the outside, so spinning around the red dot. You can see the difference in the equations. And so which one of these has the greater rotational inertia? Again, there's some different shapes depending on where the axis of rotation is and where the mass is situated. The majority of the mass, you can see there are different formulae for different objects. You don't need to know these. Check out your resource sheet and see which one is given to you. And if you need any others, they'll be given in the question. There's also a table in Howison on page 138 with these formulae on it. Go over the example and then do the activity on page 140 to 141.